G'day guys, this is part 2. The phone ran out of memory. I had to go and delete a whole heap of old videos. I've been outside, as you can tell. Hair's gone mental. But I went outside and wound my Litz coil. Now, I'm going to do this as a square coil. What I mean is equal height, equal width. I'm not going to make it into any fancy flat wound type coil because you lose depth on bigger targets. It's all right in small stuff near the surface, but you'll just lose a bit of depth. So I don't want to lose depth. Depth is important, especially these days. All the little VLFs will get all the stuff on the surface. You want to go a bit deeper. So anyway, I've made that. I'll show you how I did it, just so you know. I use the center part of that and all the bits on the outside here, which the other winding was in, I broke them off. And what I did then is I used this, as you can see, I just put some hot melt glue on it, tack, 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 and I stuck that on there like that. And I got that one and I stuck it on there like that, to get it right. And I use that to wind my coil. So you don't go, you're not going to go too big, too fat, too whatever. And I didn't wind this as you would normally wind a coil, like round and round and round and round, stop, back. I actually wound it in a particular way I do it to minimize winding to winding capacitance and also what we will call near field domain cancellation. There's a particular way you can wind it to minimize or negate some of these effects which affect the coil. So, do I have to give away all my secret sauce? Not at this point of time, but anyway, that is wound in that way. So that will fit in there nicely. All I've got to do now is tighten up the bundle, and I then have to get a low dielectric material around here, and then I've got to put my Faraday shield on, and I've got about 3, probably 4 materials I can use as a Faraday shield on these coils, and one is extremely good, and I really don't want to get out there in the commercial realm because everyone will jump on it. So I may not use the best of the best on this. I might use my second or third best even, because if I lose the coil and it gets into the wrong hands, it'll be copied, and there's nothing in that for me. So no. But that's a fairly tight bundle as it is. And I've just if you're doing a bundle like this, just go over it with masking tape. It's so thin that it doesn't really increase the dielectric constant or anything. It's paper and cottons, as long as they're really dry, basically very close to a dielectric of 1. So it's something like 1.1. It's better than Teflon. So masking tapes is fine. Even though it's got glue on it, it's extremely thin. If it was a big chunk of 5 millimeters or 1/4 of an inch thick, yes, it will have a detrimental effect, but that is not. So I'm going to rebuild this old Coiltek coil, and I'll show you how to make a supercharged, super duper coil. Now, yeah, I don't know where I got up to on the last video I was doing because the thing fell over. This came up a message and said storage is full, bad luck, and yeah, I lost most of the video. So there we go. That's it. I haven't even measured the dielectric. I haven't measured the inductance of this yet. And when you actually put it together and squeeze it a bit harder, the inductance will increase, probably somewhere between 5 and 10%. But I've got my inductance meter here somewhere. Would you believe I just got a delivery from AliExpress. I ordered just for the fun of it. I just tacked it on an order. They've given it, basically given these away. It's like, I think $1.80 or something. So I got a couple of banana leads and some clip leads on the end. It's a bit long for doing inductance, but 300 microhenries, that's not going to make any difference whatsoever. It's going to be 0.01% effect. But I will just fire this up and we'll just see what we've got. Inducted. I might have to take a turn off it. I might have put too much on, but we'll just see. As long as we're about 280, 320, it doesn't really make that much difference. Let's have a look here. On faster machines, you probably want a little bit less inductance. So we'll put it on, okay, power, and we'll stick it, it's on the L, and do it at a kilohertz, and we're a bit high. We're actually, if you can see that, we're at 323.5. So it wasn't a bad guess. And if I actually, I don't know if I can hold this up, I'll show you what happens if I squeeze the coil. I'll put that there. Hopefully it doesn't fall over. And I'll get this and I'll bend that down. And it's in the light in a particular way that you can't see it. Because I can see that you can't see it. But move that back. Stick that there. Oh dear. So glary, isn't it? But anyway, I'll pull that down a bit more. I don't know if you can, I can't zoom in either, but anyway, where is it? It's at 323. And what I'm going to do is I'm going to squeeze the coil. Now I can't see what I'm doing. No, I know why, because the clip lead fell off. They were saying over limit. Funny about that. Okay, put the clip lead on properly this time. So clip lead's on. It's going to take a while to settle down. Okay, it's 324. Give it a bit of a squeeze. Okay, 325. Squeeze it some more. 325.8. I must have done it pretty hard anyway. 325.9. But anyway, if you wind the whole thing and squeeze it, I'm squeezing the hell out of it, like that. It will go up. Not much, but it will increase a little bit. Do I actually worry about that being 325? It does give an extra, probably gives an extra turn, and an extra turn is a bigger antenna. Okay, and as long as you make this a fast coil and don't bog it down with high dielectric constant materials, it should be quite good. So anyway, we'll have a look at the, I'll look at the resistance on this as well. They're taking these very thin leads, but we'll see, and I'll drop that down. We'll look at the DC, near enough a DC resistance. I don't want to look at reactive resistance. So we'll go into there, and it's going to tell me it is, which is a load of rubbish. How can that be? There's no way known. It's saying 6.8 ohms. That is just, it's at a kilohertz. Damn, go back on 120 hertz. Okay, even at 120 hertz, it'll read a little bit high. It's saying it's 0.773. That I don't believe, because these leads must be very high resistance. What I will do, I'll unclip this. I'll use my fluke meter and do a DC resistance on it. Then we can do comparing apples with apples and not apples with oranges. So the fluke meter is, I don't know if you can see it there. So what I can do on the fluke meter is very handy. I could use a 4-wire setup on this, so I can get round the lead resistance. But what I'll do, I've got all these cans here of stuff. What I'll do, I will put it into ohms. I'll short the leads together, and this has an offset. So if I hold these tight enough, there we go. Okay, so it's just even just moving these leads around. We're moving 0.002 of an ohm. I'm not going to worry about that. So on this gadget, we'll have a look at the DC resistance and we'll see what we've got. I roughly did the Litz wire, so I'm going to do it again when I do it properly, of course. But yeah, there we go. It's about 0.5 of an ohm. It's around about right. A lot of windings I've measured, some of them people have them at 0.3 of an ohm and whatever. But you know, they go, oh, you know, we'll get more power in it. Little do they know there is a 0.03 ohm resistor inside the metal detectors on a lot of the GPX ones anyway, which limit the current, and it's used for current monitoring. So yeah, it's going through that anyway. So it doesn't really make much difference dropping the ohmage of your wire, running more wire or whatever. You can only put so much in, and you've got a time duration too. You want to just make sure that the resistance is low enough to overcome any ohmic losses getting the pulse into that amount of inductance in a given time. You can measure it all if you really want to, but I found it doesn't make any difference. I have never found a difference. Even using wire closer to 1 ohm, Litz wire close to an ohm, half an ohm, on a wind I'm talking. And the main criteria to watch out for is the stranding, how thin the strands are within reason. So to get around, all you really want to do is you want to get your coils around about half an ohm, and the cable adds at about 0.1 of an ohm. It's not much because it's just short. You got to remember on these, there's, you know, there's, I don't know how many, 26 turns or something it was. So yeah, over 7 point, you've got to, because it's an elliptical, 10 by 5, 7.5, and then you want to count the turns and get 7.5, multiply it by 3.14, and that'll give you your length. So pretty straightforward there. So will I sit here and give this a hard wind? It's boring as hell. I've got to go over it, and like I say, I'm doing a square coil. It's not going to be squashed that way or squashed out that way. It's going to be the most efficient coil there is. Even an elliptical coil is, well, it's lost a little bit of the ellipse, but I'll push it in a bit. There you go, it's elliptical again. But even an elliptical coil is not super efficient. As soon as you start squashing it, it starts having cancellation of its own generated or intercepted magnetic field. So it, you know, if you make a really skinny coil and push it right in, you're really going backwards. You're going to get near field sensitivity here, of course, because you bring the wires closer to the target, or both sides of the coil in. You're making a smaller coil, but there's a lot of cancellation, and the depth is just basically dropping away. If you get this, and I actually could show you, yeah, well, it's going to be hard because it's not shielded, but I could just show you with some targets and just you know, move it in, scream on small gold, pull it out, and you know, it'll probably still get the small gold, but your depth's going to drop off on bigger targets or anything further away from the coil. It just cancels. You can't do anything about it. There's no free lunch. There's no magic. You've got a round coil. You muck around with a round coil any which way you want. You are going to have trade-offs. It's just the way it is. So, like I say, coil making's not hard. It's pretty basic. There's some Litz wire and masking tape, and just use the old coil as a former. So usually I do a wooden pegboard and wind it on that, and have little clamps over it so it doesn't crawl up, and just hold it down, and it all stays nice, and then undo the clamps. We'll probably put a couple of cable ties around it, take off the clamps, and then wrap it up properly. But this isn't going to be the super duper coil. This is just going to be the super duper coil. Okay, it's going to be a lot better than what it was. But the thing is, you know, there's other things that you could do with a coil like this. Well, I just don't want to give too much away. I've given tons away, I really have, and I guarantee you it'll show up in future commercial designs. But some stuff there that I just don't want to talk about. I really don't, because, you know, like I say, I might get bored one day and I'm getting sick of doing electronics, and I'll say I'll start making coils. You know, I have made coils. We still make coils. We make the drag coils and that. But you know, you you can do this yourself. It's not hard. I've got tons of Litz wire. I don't know if it's on the website. I think David got sick of cutting it for people and took it off. I don't. Might have cracked it, but on our website we had Litz wire, and because I've got enough to go around the earth about 500 times, that's that stuff too. It's the good stuff, and yeah, I don't know if it's still there. He doesn't like, people say, "Oh, can you cut me enough to make an 18-inch coil?" Oh God, you know. No, you're gonna, if you want to buy 100 meters of it. Don't buy 25 meters or something, and then you'll go, "Oh no, it's one turn short. What do I do?" Oh. No, it's you got to be careful with Litz wire. What I suggest, guys, if you're mucking around with Litz wire, because you can't cut it and join it, it really goes to pot if you do that. You've got to keep it as a Litz structure, only soldered on the ends, right? Don't cut it in the middle here and you add a bit and then stick it there. You can, but you'd have to put a you can, but you need to put a little very, very thin walled, basically, I'm just thinking of the what you'd need. You probably want to go for not field absorption. You want to go for field redirection around on the ferrite. So you'd probably utilize a proper type of ferrite, you know, high frequency ferrite, something that works around about, I don't know, 25, 50 kilohertz or something. But you can do that, and then that blob of solder won't interact with anything around it, because it'll sit there and it'll just generate eddy currents. But if you even just put you can get some iron powder and mix it up in glue and just paste it around. It will work to a degree. But yeah, you don't really want it to do stuff like that. You want your Litz wire as a complete run, not cut and joined and stuff like that. Don't do that. That's not good practice. And I've never done it. And would it have an adverse effect on the coil? Yes. But if you did do that, what I would do, and this is just logical, right? Because I know people will do it. Now, say my hand is the ground, okay? You don't want your join here. Put your join on the top, okay? Put your join up the top here so it's away from the ground. So that's just one way of probably mitigating the effects if you balls it up and have to join your Litz wire. But with Litz wire, what you could probably do, get some El Cheapo wire, right? And I mean El Cheapo. Someone's playing computer games with their friends, all online, screaming their head off. Fantastic. So that's why I usually shut the door. I come back in, I forgot to shut the door. Yeah, so yeah, wind your coil out of normal wire within reason, depending what the dielectric is on the wire. Because what's going to happen if you have a high dielectric, like I don't know, PVC wire, it's going to actually, if you make a coil and then you make, say it's got too much inductance and you cut it and take a turn off, and because it's stranded wire, you can just measure it easy, right? The other way of doing it too is get a LCR bridge and stick a needle on one end and just push it into the wire so you don't have to cut it. The rest of the wire all hanging off the coil is not going to make any difference to the coil. It's not going to increase the inductance, going to have no effect. So you can actually just say, well, I've got all these, I'll stab it on the last turn. Oh, no, that's too high. Take some turns off, stab it again. Oh, that's, 280 or 300. Oh, good, snip, away you go. So you don't lose any wire if you're using a insulated tin-plated wire. This wire is different. You can't stab that and measure it. You'll wreck it. You can't do that. It's quite critical. So, yeah. Now, what we need to wrap this with a low dielectric spacer. Now, what will you use? Foamed material is probably the best. Basically, like how the coils are made by the commercial people, they route the end of their round bits. Have I got a bit? Yes, I have. I've got another one here. I was going to wind this up too. This is a Sadie. I was going to give this a treatment. But see how they just route in there? Put it on a bench and just, route it round, whatever it goes in. Wind the wire in. And yeah, this one had silicon stuck on it holding the wire. Naughty. You don't use silicon. A high dielectric constant of about 8 or 9 or something. We don't do that. I don't do that. Okay. Use foamed material. Tell you a good one to use. Have I got it here? Yeah. Hang on. Yeah, nah. No, yeah. I have. See this stuff? You get this, I don't know. I think you get it from sewing shops or something. I don't know. But this is a foamy rubber, but it's double-sided. So you take the paper off here, and yeah, it's really tacky. It's good to do. You could probably use something. I get the single-sided one of this because it's foam, just light as a feather. Just feels like it's made of cork or something. But it'll have very, very low dielectric. If you really want to measure it, you put it between two, say, 1-inch square plates, and yeah, sandwich it and put it on your capacitance tester, and it'll tell you the dielectric constant. You'll work it out. Basically for your thickness and plate area. But don't need to go into that because it's getting ridiculous. But some foam stuff, lots of air in the structure. That's what you want. You want air, but you want it to be so it doesn't move. So that's why all these coils, like, crispy foam, it's hard as a rock. So that's what it is. This one too, I'm gonna use this bit of foam because it's already routed nicely. But what I'm going to do on here, I'm going to sand all that black stuff off and redo it. So it's another project. I'm going to make some good coils. I'm going to make like a super duper coil, and I probably might make a super duper duper coil. Right. And I think I might have a spare Coiltek one kicking around somewhere where I'll be able to do a comparison side by side. So why not, eh? Why not? So anyway, I've got to scunge around the place out in the garage now and go and find the spacer material I want to use. It has to be, well, it's got to be stiff. It's got to be full of air. So like honeycomb. It's got to be like honeycomb, basically. And, you don't want any movement. As soon as you have movement between any of the wires, right, they all start wiggling around. The slightest movement, I'm talking fractions of a thou of an inch, it will make noise. It will make the woo-woo sound in your detector because it'll just change all the parameters. So that's going to be really tight, really, really tight and bundled. And the Faraday shield spacer, which you got to remember too with Faraday shielding, you can probably have thinner Faraday shielding spacer at the bottom of the coil. It's closer to the ground if you're looking for, pinhead stuff. And the rest of it can be wide spaced because it's not going on the ground, which will also reduce the capacitance of the coil. I see all the commercial coils, they go equal spacing there and there and there and there. And I say, well, why are you doing that? It doesn't have to be. You can have it close spaced on the bottom, close to the ground, and very, very thin ABS too. Very thin ABS sheet, right? And get it close to the ground. Because, you know, if you go raking, right, you rake the ground, all these nuggets pop up, and you only moved a couple of millimeters of little pebbles. Same effect. Yeah, get your coil close to the ground. So what you gain in capacitance here by having your Faraday shield closer, you can negate that by having it out further here, and further there. So, you know, you've got three sides, if you want to look at it as sides, that you can expand the shielding, but you can offset that closeness here by spacing these. So the capacitance drops off on these sides. It'll obviously increase here, but because you're offsetting that increase out here, it stays the same. And you'll get a gain of 1 or 2 millimeters, something like that. But it's true. It's just the way these things work. You want to get the coil as close as you can to the ground. And there's other things too. Even doing the Faraday shields, you don't really need a great whopping shorted plate of graphite material across the whole thing. Just remember, you want to protect this. You don't need to protect here in the middle. You don't need to, you just got to have it around this here. So, if you look at a commercial design, you can probably say, well, look, it runs off here and over here, so there's no capacitance here, right? You could look at it that way, but there's nothing stopping you running it out here and then shielding it on this side out here or there or there. You don't want continuous carbon or anything partially conductive or totally conductive or anything like that. Always look at this as a transformer. Okay, so if you want to say you made a transformer, you made 2 of these coils, and you put another one here. It's only air core, but at a fairly high frequency, you can put in X amount of power here as a AC waveform, or square wave if you really wanted to, and one here just next to it, you'll be able to get equivalent amount of power out, probably somewhere around about, depends what frequency and how it's all constructed, probably 95-97% efficiency. So that's how a transformer works. You go and you do that and go and put a shorted turnaround here, just a loop of wire that's connected, on the end. It's just so it's a continuous loop. Put it there, and you watch the energy just disappears. It'll short. Whatever's driving this will overheat. It is terrible. So treat graphites and carbon like a shorted turn. It just will rob your energy. It'll take it. It'll take away. Not that you can measure it. It's not going to glow red hot in the dark because there's not that much power there to start with. But it can affect fringe signals by burning up the power. So just yeah, I should show you all these photos. One of the guys on this he watches these videos. He's been making his own coil. He had a Sadie coil, and I think it's a Sadie, a bigger one or something. I don't know. It's grey anyway, so I'd say it's a nugget finder that failed, and he's rebuilding it. And he's showing me all the pictures of how he's building it. And the way he's doing it actually is really, really good. Should be a really good coil when he finishes it. So wait and see. Anyway, I'm going to have to go and look for stuff, so I'm not going to continue making the video. So there'll be a part 3 of this video when I do all the shielding. So leave it there and catch us.